All right, so it's my pleasure to have Matthias Zach talking about some Le-Greuel formula of stratified spaces.
Yeah, thank you. I'm very happy to be here and given the opportunity to give this presentation. The title does not suggest it, but there are some characteristic classes appearing. You will see. And as you could already guess from the discussion, I wanted to have this on the archive so that people can look and we get, if you have some ideas, talk about it. And I think it appeared this morning or even yesterday on the mailing list already. So let's have a little look into it. I have to get acquainted with.
Ask Agustin to explain you how to do it.
Yeah, the other button. So I wanted to start with the applications, and the applications are very classical application. As Lorenzo also mentioned in his talk before, we count most critical points, right? So suppose you have a singular variety. In this example, I need to be very simple so that I can still draw pictures. Say this variety. It looks like that, at least the real picture. So I put the x-axis here, the y-axis upright, right, and the z-axis comes here to my face. And then I want to consider holomorphic function on the ambient space, let's say. In this example, I would like to choose this. So this function obviously has no singularity on C3. Right? Here is a very perfectly fine linear term. But when you restrict to the singular space, then you get a singularity in the stratified sense. Right? To have something in the stratified sense, you need to choose a stratification, like in this case, obviously the smooth part as one stratum and the one point stratum at the origin as the other stratum. So here you have the level hypersurface, the x to the 3 graph, and its intersection with x, and here you already get the idea why this is singular. If you perturb it a little, you will get something which looks a little different. So you want to study the Milnor fiber of this function, which, yeah, you all know how the story goes. You choose some epsilon, you choose some nearby value v with which is sufficiently close to 0, then you get something that looks like this. Right here, the real picture, two parabola-like objects. So in this example, it's evident that, well, the function just substitutes y by x to the 3. And then if you do this here, you get an A3 singularity, right? It's x to the 4 minus c squared. So you know what the Milnor fiber is in this case. And it's here 3 spheres of real dimension 1. Or up to homotopy, it's 3 spheres of real dimension 1. Yes, here I put the equation for the hypersurface. So I chose an example where you have other means to compute the outcome so that we compare, right? But what we should have in mind is function on a singular space.
But maybe we should emphasize that, of course, the restriction of a function has a singular point, because stratification, zero-dimensional point always counts as a singular point.
Yes. In this case, yes. But the singularity could be more complicated, but then I think...
No, but as soon as you work with stratified spaces, the convention should be a zero-dimensional stratum is always counted as a singular point.
Yes, that's basically the effect.
That's important
to see here. Yeah, but if I chose a more complicated function which had a worse singularity than that, then yeah, the pictures would become too complicated. Right? And it also has a reason. I will show some computations later, and unfortunately the computer is cracking down on more complicated things at the moment, so we need to work on that. So coming back to this example, we want to be able to verify or to do such computations more generally. Right? So also in cases where we cannot say, ah, yes, after some substitution, we are in the classical case. So what we can do more generally is we can choose a morphification, right? So in this case, we would perturb by some linear form. In this case, this is sufficiently generic. And then we get a story which looks like this. Sorry, that's a little bit. Ah, yeah, okay. So we pass from the original f to something where we wiggle a little bit in T, and we get a hypersurface like that. And what you need to observe is that when you have the nearby, the Milnor fiber here of the original function, and you perturb a little bit with this T for the nearby fiber, you get something which is isomorphic to the Milnor fiber, right? And then you can start your morphification process, and you get critical points. Here, one critical point on the top stratum. Then you pass that point, some attachment happens. And here's what Jörg pointed out. When there's a one-point stratum, it always appears as a critical point. Okay? This is something different from morphification in the smooth case. And then there's another critical point here on the backside, right? And you get an idea, yeah, it's the same thing that happened before up in the front here. Right? So what you have to observe is there are critical points, and they belong to the strata. Yeah? They occur on strata, and you can collect them stratum per stratum. So what you get is Milnor numbers for the function and the stratum. So mu of f and alpha. And what you have then is, this is actually not one theorem in the literature, but this is Tibar's bouquet decomposition theorem for such hypersurfaces, functions on a hypersurface. So for functions on a singular variety, but functions which take values in C, right? And he has not done this for morphifications, but he told me that Massey claims to have proven that the numbers in his bouquet decomposition are actually the same numbers as you get from morphification, and I think Massey proved it.
It's complicated.
Yeah, and you have given a more direct proof.
But only for isolated stratified.
Yeah.
That is the
Yeah.
case he's studying now, otherwise you even don't speak about
Yeah, yeah.
modification.
Yeah. By the way, is that published already? Because I only found the archive version.
I think so.
Okay, then I should update.
But if you say you allow to weakness and you don't really want to have it as an homotopic decomposition, but just say homologically or cohomological,
Yeah, then
it's much easier.
yeah, then it follows from the morphification thing, but you have to combine some theorems to really say how to homotopy you get a contribution.
If it is this homotopy, you have to work, for sure.
Yeah, but the work is done, right?
There are
So
two different contributions, two different ways of realizing this. You just compare stratum by stratum.
yeah. Okay, but this is my colloquial summary of what you can do, right? So what we want to have is an understanding of the stratified Milnor fiber, and we need these numbers to get this bouquet decomposition of what we get out. Okay. No, I'm going back.
Did you
Sorry.
introduce a notation? What I think this
Ah,
is a
yeah,
complex
this-
link what you take there, yes?
You're perfectly right. I should say this. This is the complex link of x along the stratum. Right? So for the zero-dimensional stratum, you just take the complex link in the usual sense, yeah, which is the Milnor fiber of a linear function, generic linear function. And if you have a higher dimensional stratum, which we do not really have in this example, I'm sorry, then you first take a plane section which is transversal to the stratum, so that you're reducing to the zero-dimensional case, and then you play the same game. That's the complex loop. And in stratified Morse theory, it has this central role that it encodes the normal part of what you're attaching for a most critical form. Right? And this is supposed to mean the default suspension, or the default double suspension. And d of alpha is, I will write d of alpha for the dimension of the stratum. Okay, so why is this number well defined? Well, it could depend on the chosen modification, or could be many things. But one way to see that this number is well defined is, for instance, by a theorem by Pepe and Mihai Tibar and Berdiowski, which I think another version has also appeared in your talk before.
This is a relative.
But this is the global version.
This is a relative one. Yeah, it's a global.
You have the version on a global affine. So what you are taking is a local on a small ball,
Yes, exactly.
and you can do the same way they do.
Yeah, and I think you have there are two papers, one for the global thing and one for the local.
There is a
Doesn't
point
matter.
in Mexico.
Okay, good.
Brazil.
Except
Right?
But since you only want to control the numbers, you can do by the machinery of characteristic cycles. It's an exercise.
Yeah, okay. I'm not saying that this is the proof, it's just,
No, but the thing is, these complex links which you introduce,
yeah,
they give more or less in the language which
Micro
in the talk, these characteristic cycles. He said we have multiplicities to the conormals, and with the sign convention, these multiplicities are exactly the Euler character of the normal of all. The reduced Euler character is a complex link of the normal Morse data. They give you the multiplicities in the characteristic cycles. And if you can formulate your, but we can discuss that after your talk.
yeah. I mean, there are this intersection theory from the conormal things which give you the same numbers.
This automatically.
That's okay, but I would like to pass through this theorem because it fits better with what follows. I'm not working in the conormal setting.
And the other thing is it should not be in Euler F. Is it in Euler F what you have written?
Yes,
That's
it's
the
the Euler obstruction of the gradient field, which is adapted to the stratification and that thing. So in that paper, it's for gradient vector fields, right? But you can do similar thing for the differential of f, so for a one form.
relative one.
You,
I will explain what this is.
I see now. Yeah, I see.
So here I write x alpha for the closure of the stratum, okay? And I want to, I mean, I prepared this talk with, I probably didn't think properly of the audience. I think I don't need to explain to you the details, but let's just review this very quickly. So you take as usually, the Nash modification. So on the regular part, you get your Gauss map, and then the closure of the graph gives you this Nash modification with a natural extension of the Gauss map, and I will denote by T tilde the Nash bundle, and by omega 1 tilde the dual of the Nash bundle, right? And then what is this Euler obstruction that you see up here? Well, you take the gradient vector field down here, and I made an attempt to really draw the gradient vector field, right, of this function that we were considering before. And when you make everything tangent to the stratum, you get something like this. You pull it back upstairs, right, and modify it a little bit to have a section of the Nash bundle. And then next step is you try to extend it as a nowhere zero section to the interior. And then, as usual, you will encounter difficulties, like when you try to comb your hair. Everywhere there will be some special points, and that's what's being counted. So that is a procedure which is nice in
But the
theory.
important point, maybe I should emphasize this. Important point is, of course, that you start with the stratified isolated singular count,
Yeah.
which guarantees you that by Whitney B, if you take a small sphere, or no, here you
Whitney
have
A.
isolated. You have no critical points on the boundary.
Yeah.
So that upstairs you really can start abstraction theory on the boundary, nothing is happening. So this argument only works for isolated stratified singularities.
Yes.
I think you can rephrase this to nearby cycle.
No, that is the other papers our people have done. But this viewpoint needs the input stratified isolated singular count.
Unfortunately.
Just to emphasize this.
Yeah. Okay, but this is a very topological definition, and these definitions are nice in theory, but horrible to work with in practice. I don't know a single person who has ever computed an obstruction by hand, but maybe in very simple examples. So, if you have done this computation, you also don't write it in the paper usually. It's horrible to write it up, right? So, what if we had something else to do the job for us? What if you had a complex, right? A complex, some modules, some maps over a ring, and here I want to have the convergent power series at the origin of the ambient space and some parameters, right? So some polynomial parameters. And the complex could look like this. So here 3 modules of some ranks, some maps, yeah, which will be represented by matrices. And then this complex should have the magic property so that after substituting for these parameter variables, then we get something over the ring Cx, which computes this Milnor number, or this obstruction. That would be good, because this we can feed to a computer, and the Euler characteristic is just a monomial count for Grödner basis things. Right?
So one should see this as an analog of the algebraic definition of the Milnor number.
Yes.
Jacobian idea.
I mean, you know where this is going, and
No, but Milnor fiber in Emersdorf, we already started before.
yes,
That you have the Milnor fiber and you have this topological definition, but we also have the algebraic definition of the Milnor number.
yes,
Yeah, and
Yes.
that should be a kind of analog for this new Euler obstruction of F.
yes.
That is what I want to say. That is
Yeah.
what you want to say.
Yeah, I mean, this is probably not a very common style to say. I wanted to make this a little more surprise, right?
Oh, I didn't want to steal you.
But so, what if you had such a complex?
You know,
Right? Yeah.
So when you say Grödner basis, usually this is associated to an ideal in some polynomial ring, right? So you have to define the ideal here.
Do it for a
It's a
module.
Grödner basis of what? Of some ideal.
No. Okay. First of all, this is local, so I should say standard basis, and then standard basis of modules. But there's a theory of standard basis for local monomial orderings, which extends the Grödner theory, which is probably not very common in Macaulay too, but in singular has been driving force, as I understand.
Actually, so you put some ordering on these variables, and then you define some ideal given by something, and then you group them and it generates somehow.
No, I mean, in practice, you will have polynomial representatives for this whole complex, right? And then these are just 3 modules over polynomial rings, and you can compute homology here, homology there, and you take alternating sum of the vector space dimensions. That's
So what is the Grödner basis?
the Grödner basis is in the background when you compute the vector space dimensions,
I see.
right? because you need a standard basis, and then all monomials which are not in the leading ideal, they form your vector space basis. That's where it enters. But this is computable. So, what if you had such a complex? That would be nice, I think. So, here's the complex. It looks like this: 1, 9, 16, 9, 1. So a little bit binomial, but not really, actually. And then you have these matrices here. And I'm sorry, I had to go to 1 dimension higher here, because yeah, the computations were done in 1 dimension higher. This was more natural, but I wanted to do the pictures in 3 dimensions. But it's basically the same thing. So the matrix looks, for instance, like this. This is the first matrix here. It goes from R9 to R1, and due to the Oscar convention, where I did the computations, vector matrix multiplication comes from a row vector here to matrix. Sorry, that's how it is in Oscar. So you see all these parameters, but you also see the variables from the base ring, right? And the next matrix looks like this. It's a little more complicated, or no, actually not more complicated, but bigger. And then something which I cannot print in full extent, so I abbreviated a little bit, but I can give you the matrix. And here's the last one, which is just a very long row vector, because the entries are each rather long. And what this is a homological index, which we also saw on the first day. I would like to think of this as a homological index, right? And there are various papers on these ideas of homological index, and by Javier Gomez-Mont, and I think by you, Pepe, and some others.
And in your language, I remember what was the substitution? You take the gradient, so it would be a kind of analog of a homological index for vectors. What was the substitution you take for the variable? It was dd.
The partial derivative of f. So here's the theorem from some years ago for this case of a function taking values in C, and I slightly modified it to adapt to the notation of my preprint from today. So here's the isolated criterion that you need. If this has an isolated singularity on X, then this Milnor number or Euler obstruction is computed by, you take a sheaf, or a sheafified version of the Koszul complex from the pullback of the differential of f to the Nash modification. Then you take derived push forward and the Euler characteristic of that whole thing. Okay? So here I wrote for you the sheafified version of the Koszul complex. So you take the Nash bundle and its exterior powers, and then you can define a contraction with the one form. Usually you take contraction of one forms by vector fields, but since on the Nash modification you have a vector bundle, then contraction can go either way, right? Vector bundles are self-tuning. You're in a good setting. So you can just define this.
And working with the extension of the tangent bundle is a more natural one to fit in with your original obstruction definition, like a McPherson's paper.
Probably.
Yeah.
Yeah. Now when I wrote up this paper, it's more natural to do it this way around. Also, you have less sign -1 to the dimension something floating around. It's much more convenient to.
Do you really need this derived push forward? I mean, this is all a characteristics of pushing forward to a point anyway.
No, I'm pushing forward to the original x, which is
Sure, but since you're going to take all the characteristics, then you're also pushing forward to a point from there. Right? This is a composition of mass. So this is the same thing. I guess I'm claiming that this is the same thing as the other characteristic of the Koszul complex. Because there is like the Grothendieck composition of functions.
So you can calculate the Euler coverage upstairs or downstairs,
Yeah.
it doesn't matter.
It doesn't matter.
You can calculate it on the Nash cloner.
Or on the,
It's supported above the singular fiber, so it has homology is on a compact analytic subset. So it means it has global finite dimension.
What does it mean to compute this upstairs? You need to.
it means that push forward to a point.
You are calculating Euler coverage of complex, and the question is where you want to see this complex. Want you to see it on the original X, or because you construct it on the Nash clone up, you want to do it on the Nash clone. It's a matter of taste what you want. They both give the same Euler coverage.
Yes.
You want it pushed up first to the original space. Your device push forward.
Yes.
And what he was mentioning is you can delete this device push forward if you want. The Euler coverage is not changed. Once you calculate the Euler coverage for a complex upstairs, which is acyclic outside the fiber over the singular point,
Yes.
and if you push forward is, you get a direct image complex, which is acyclic outside this point. The Euler coverage you calculate is the same for both.
Yes, but to compute it upstairs, I need to go through some
That's
homology
the question.
computation.
That's
So you
the
only
question,
want
which
to-
one is better to calculate?
Yeah.
So
So
it's effectively the same calculation, isn't it?
I don't know. So I mean, these are the same quantities.
I think the
Given.
downstairs
The question is where you want to calculate.
downstairs the advantage is of course that you're working over local wing, which maybe you need for your computer program. Upstairs, it's a global question.
Yeah, it's global in the fiber
the fiber.
direction, but local in the other direction.
I know,
So,
I think it will not make a big difference, but I think if I understand Leonardo's comment, that was the comment.
Yeah,
You can use
Just
upstairs
put-
or
yeah,
downstairs.
yeah, it should be the same thing. Only that if you write it like this, then you can think of it really as a complex of sheaves downstairs, right?
Yeah.
So.
So maybe one other comment. Yes.
Okay.
Of course, you started from the stratified viewpoint, and you want to have the function, or put these things together in your wedge decomposition and so on.
Yes.
But as soon as you go to this picture, you can forget about stratification, so you work only just with one closure of the stratum.
Yes. You have to do this for every stratum,
Yeah,
right?
you have
For
to do
every
this for every
stratum.
stratum, but in principle you are back then to the situation, you don't need really the rest of the stratification. Because you make this all obstruction relative to the given stratum that does not measure the other ones. So,
Yes.
yeah. So in principle, you can start with an irreducible analytic set with a function in a stratified other sense, but you only want to calculate this Euler obstruction of F.
That's true.
Yeah.
Okay, so I'm already half time here. I think I should hurry a little bit. So I want to show you some new results, right? So that was already some years ago. So after that, I thought, well, there should be some extension to something like complete intersections, right? But then, for some reason, I didn't see exactly how. There are some papers like Euler obstructions of a map with, I think you and Nivaldo, and probably someone else who I forgot. I don't know. So people have been trying to do these things. Also, Sabir Hussein-Zadeh and somebody called Gorski, who I don't know in person, have
Gorski?
Yeah, done some things. But yeah, I wanted to talk about the generalization when f takes values in. Whoops. This is what happened to you, right? It jumps to a random thing.
I should only have
So-
one, eh?
You know, there are only 4 buttons.
Yeah, but
Yeah, but one of them is the random button.
maybe it changes from day to day.
Maximum likelihood.
Estimate.
So what do you do if your function takes values in CK? And first thing you have to make up is building the background theory to say what are the Milnor numbers in this case, right? And what does it mean to have an isolated singularity? So Pepe and Juanjo and Le have some work in progress, which is also in the Juanjo has talked about this in Mexico this year in the summer, where they are considering vibration theorems in this context. So I want to stick to a very simple definition, which is not so general, but it's doing enough for me for the moment, right? So I will say that such a function has an isolated singularity on X in the stratified sense if this degeneracy locus of the differential, right? You take the differential, you restrict to every stratum, you know what it means to be degenerate there. Whitney's condition A says this is actually closed and not only locally closed. And you take this degeneracy locus and you intersect with this with the central fiber. And you say this must only be one point. This is completely analogous to ICIS.
Yes, so if the ambient space is smooth, one stratum,
You recover the ICIS definition. Right? Problem is, since you don't know anything about X, you cannot speak of a regular sequence or anything. I have to avoid doing this. Right? So F is just any function.
But you want to introduce a Milnor vibration. That is the easiest way you want to speak of a Milnor vibration.
Yeah, I mean,
If you want to do it more generally, what you need AF stratification, which are complicated to get if you are not for a function with one variable.
exactly. Yeah, and that's more tricky. But here, when you do a definition like that, you can avoid a lot of difficulties.
Yeah, this is the starting point.
Okay, and then you can prove that you have a Milnor fiber, and this Milnor fiber has a very similar Bukidin composition, right? And actually, this is just an extension of Mihai Tibar's Bukidin composition. And in his paper, he has already given some hints how to do it on a smooth space, and you just need to piece things together. So I should be maybe a bit careful here. I put a star because I'm not sure that I can claim really originality on this, but I would be happy to discuss this if you have opinions on it. I had the feeling that I had to do it because it was nowhere really written down to this extent. So you have a bouquet, complex links play a role here, and you have these mu alpha f's which count the contributions on every stratum, and here you have something that I like to call the complex link of codimension k, which is what you get when you, for the usual complex link, you take a hyperplane. For the complex link of codimension k, you take a plane of codimension k, and you move it a little to the side. Right? So it's the object that you get then. So the takeaway is there are Milnor numbers, and we want to compute them. We want to be able to compute them. And this is the theorem which is doing the job for us. So if you have, this is just a repetition of the previous setup. If you had a function with an isolated singularity in a stratified sense on the germ X, then you get formulas like this. Right? So what you see here is, again, you do the Nash modification, and then you do a pullback of some functions. The L1 up to Lk will be linear forms, sufficiently general linear forms, and you can form the Koszul complex of a collection of functions, right? And do this on the Nash bundle. And here you get the Egan-Northcott complex. The Egan-Northcott complex is a generalization of the Koszul complex. And for the Koszul complex, you put in 1, 2, 3, 4, 5 functions. Then you get a complex. For the Egan-Northcott complex, you put in a matrix of functions. Right? And this actually sheafifies. So you can build an Egan-Northcott complex of sheaves on the Nash on the Nash transform. And then, well, yeah, you have these two terms
important point is, of course, besides structures, these complexes, that you have to inductively about the numbers of your functions. I see. So you go from f1 to fj minus 1, and then you go to the next. And so that is, I guess, what is motivating your title. All type formula or something, so like in the intersection.
Yeah, the classical Le-Greuel formula, they compute Milnor numbers.
Yeah,
right?
In this way, you have to order your functions and you make it inductively. Similarly. I don't want to claim it's the same, but
the thing is that the classical Le-Greuel induction, it only makes sense on stratified spaces which have the right rectified homological depth.
Could be.
Because otherwise,
I don't want to claim about the idea of proof or something. I only realize that I would guess you need this to have a chance that inductively you work with one distinguished function you're working to use the function situation on some cut down space.
I'm going to get to this, right? For the moment, these two terms are very similar. The only difference, and I'm afraid you will not find it unless I put it in some color. The only difference is that you replace df by dl, and you do this, as you said, inductively. So you go from j equal 1 up to k.
So should I? Of course, I don't understand these terms. I only look at the structures. So that means, because you take these two terms with dfj, would be you fix the other situation and you with your fixed degree j and look for a modification picture of this fj.
Yes.
On a restricted situation.
Yes.
And you deform this dfj to your dlj and try to make out.
Yeah, we'll get there. So this is not the only formula. Right? I said my title was several formula.
Yeah.
So this is another one where you do a very similar thing, only this time you change the first one of the two. You change one fj for one lj. And this is actually the proof that Mihai and Laurentiu have written up. That's what's behind it. That you have the original definition from the carousel and the morsification, right? This one you get from the morsification, this one you get from the carousel. And there's a third one, but we don't have space, right? The third one is following the original Le-Greuel strategy of proof.
But I even don't remember the formula exactly, but I only wanted to say there's a kind of inductive that you do fixing some functions and do the next function.
Yeah.
And I think that is a general principle on higher dimension situations.
Yeah. So the order doesn't come in at all.
Which order?
The order of the functions.
No, it will not. It will be independent of the order.
The left-hand side is.
The left-hand side. Yeah. And that is the reason because you have a global Milnor function.
No, I have to admit I thought maybe it comes here, but the L's need to be sufficiently generic, and you need to do one generic change of coordinates in the codomain in the beginning, like in the classical Le-Greuel formula proof. Right? So, yeah, this I swept under the carpet, but I should say it. Right? And it's in the paper, it is, but I didn't want to clutter these things here. So, let's move on a little. So, there's one theorem at work in the background which has to do with obstructions again. So, if you have the thing is, you saw these formulas, but they are all built up of the same building block, right? So there's one theorem which takes care of interpreting this thing, and that can then be applied, for instance, in the Le-Greuel setting. So if you have any function and a collection of one forms, so just one up to m1 forms on the ambient space, and you have this very familiar non-degeneracy or isolatedness criterion, then you have a theorem. You have this theorem. So you can choose something like a Milnor ball and a delta for the codomain. And then you have, for some technical reasons, you have to restrict the possible choices of your regular values for the function a little bit. But then you can choose a nice regular value, V, and you can take the fiber, which is not a manifold, but a nicely stratified space. And you can play the same game. You take the Nash modification and the pre-image of that fiber under the Nash modification and try to extend this M frame as a nowhere degenerate M frame in the dual of the Nash part to the interior. And Theorem says that this obstruction, this topological obstruction, can be computed by this holomorphic Euler characteristic.
I think I missed. You're saying this Euler characteristic is non-negative. Also, you had it on the previous slides.
Yes.
Why is this?
Because you're taking the obstruction of holomorphic section, and there are no negative intersection numbers in that case.
So this comes from the left hand, from interpretation. That comes not from the algebraic formula.
Yeah, the algebraic formula does not give it to you.
This
but
comes from the geometric
it's
interpretation.
really the interplay with the topological side which is giving you the strength here. Also in the proof here, I mean, a priori this, I have it on the next slide. Let's go there. So you have a situation like this. You have some central fiber which is horribly singular even, right? It doesn't need to have isolated singularity. Remember, it was any function. And some frame, in this case vector field. Right? And it doesn't need to be tangent vector field or frame or anything. The vector bundle in which, it's one force. So they can point in any direction. Then you pass to the fiber of a regular value, a good regular value. It could look like this, and you try to extend to the interior. But for another regular value, it could look like this. So it's a priori a little bit weird that both should give you the same obstruction to extending to the interior. One time you have this, and the other time you have that. But I think it's the case. I think I proved it.
But then let's go back. How generic you have chosen the fiber? With your theorem. How generic you have to choose E?
Well, technically, the problem, what's happening is that you have to take the Nash modification of your x of the space, right? And then you pull back the function there, and what you actually need is a regular value for this pulled back function.
But that is the advantage that you're working with forms, so with differentials of functions coming from the ambient space, because that you can easily move around and pull back to the Nash plane.
Yes.
Because, of course, there are some similarities. I think that was already the definition of the Euler obstruction of the holomorphic function unit. It was motivated to be very analog to the original definition of the Euler obstruction. Yeah? Or if you think about Marie-Lane-Schwartz's definition of measuring radial vector fields and so on. I think it was also inductively, and the radiality was only in the last coordinate in your frames, I think, in the construction. And she was, of course, restricted to need stratified tangent vector fields and so on. That was a vector field definition. This is infinite. But you are working with forms, you are much more flexible. They come from the ambient space. You can move them around. You can pull back to the Nash plane, which is much easier.
Yeah, sure.
That is why here the form is a natural version.
For me, yes.
Yes. Yeah, I want to say for everyone.
Especially, I want to do computations.
Yes.
So if I work with vector fields, I would need to find adjustments along the strata and stuff.
Yeah, no, that will kill your idea with your what you want maybe already.
Yes.
Okay.
So let's continue. I'm already running out of time, so let's be a little bit quick.
But we have time. We are not in rush.
Yeah,
We started in between the discussion, and we take the time from the discussion out. Don't take it easy.
Okay. So this is to illustrate the surprise part of this, right? But yeah, so in particular there is a corollary, or I claim that there is a corollary. We can pre-compute this whole procedure of doing the Nash blow up, pulling back, taking derived push forward, right? You can postpone the substitution. You can work with formal variables, like one CL variable for every function, for every component of the function, and some other variables for the matrix with which you will build the even Northcott complex. And when you do that, basically the proof should go like this. You have your sheaves of modules which appear in this stratified version of the Cauchy complex times even Northcott complex. They depend on the Nash bundle, right? You can cook them up from the Nash bundle, but you don't need the this F and omega for the modules themselves. The only thing that varies, that depends on them, is the induced maps. Right? And then you take derived push forward, so you get the double complex, and the columns depend on the modules, and only these horizontal maps depend on the F and the omega. And the final result is just the total complex of this double complex. So you get Q1. This preparation complex.
To go once back to the theorem, so
Which theorem?
yeah, before you do this for these functions and collection. So what is lambda?
Lambda is just it appears here, right? It's in the text. It's the obstruction.
Lambda is the obstruction index.
Yeah.
Okay, lambda is the obstruction index. But why is it here a priori clear that it does not depend on which fiber you are taking?
It's not clear.
It's not clear. That is the point. I want to say you do it for a fix. You choose and then you make this.
No, the content of the theorem is, in the end, it is. It's part of the theorem that is independent of the fiber.
Because your complex does not see the fiber anymore.
Yes. You use conservation principles, and then you have a moving lemma, which says if V is from that nice set, which is dense, so you can always take a little step to the side and be there, then you get the same Euler characteristic.
Yeah, but from which side you see this? From the topological side or from the algebraic side?
You have to see it from both sides.
From both.
And then this is the strength. You have to combine both sides to get what you want. So yeah, and I wanted to advertise this because I think it has some more generality that might open up applications elsewhere. Okay, I wanted to show you an example of these complexes. Or no, okay, first some how you prove this main theorem. So first you need to show that the statement makes sense. So that there is a stratified version of the Cauchy complex, a stratified version of the Northcott complex, and so on. So then you establish a modification lemma or a moving lemma, which says we can construct a deformation of the function, a deformation of the collection of one forms, so that everything is in sufficiently general position, right? So here you get the fiber of ft for t non-zero and omega t for t non-zero, and you need isolated degeneracy point of this collection of one forms. And the fiber might still have singularities, but no degeneration of the collection of one forms there. This is necessary. And you can prove this, and then you apply this principle of conservation of number, which is a paper by Javier Gomez Mott and yeah, thanks. So, and then you can see whatever deformation you do, the Euler characteristic, the holomorphic Euler characteristic is the same. And if you happen to be in a fiber which is in this general position, then you can combine the findings of the sheaf side here with the topological findings of your morphified situation. And then what you see is that here the parameter is 0, here the parameter is t non-zero, and this side splits up with as a sum over all points in. I should have written here x. Sorry. Over all points in X in the holomorphic Euler characteristics there, and this is actually here the points where you find where you can localize the obstructions for extension, and then you just get from this part that the obstruction contributes 1 and the Euler characteristic contributes 1, so both sides must agree. So I could say some words on this, how to prove this bouquet decomposition theorem for maps to CK, but I think we will skip that part. Or does anyone want to see this in particular?
You can move it to the discussion.
Okay, so it's there if you're interested. So better see one example. So this is basically the example from before. So I like to work with these determinantal singularities, and in this case it is because I know how to compute the Nash modification. So let's just take this very simple case. Take a function on this space of 2 by 2 matrices, and also a very simple one. The first component just says consider the symmetric matrices. The second one says consider this what we had in the earlier example. But this is a complete intersection on a stratified space because you restrict to the space of degenerate matrices. And in this case, this preparatory complex has several parameters. One parameter C for this guy, the first component of the function. And then you have a Jacobian matrix, which has 2 rows and 4 variables, so 4 columns. Then you need to put 1 parameter for each entry of this matrix. And then you feed it to the computer, you do the Czech cohomology computation, you take this derived push forward, you get a complex of modules over this ring. And this is in cohomological degrees 0 to -5. And again, you get a lot of matrices which actually don't look too bad. I mean, you don't want to do this by hand, but it's not horribly complicated, right? So, yeah, this is one entry, right? I couldn't write it in one line. So this is one entry, this is the next entry, this is one entry. But it exists, it's complex. And then here, the next matrix, next one, and the final one, the 2 by 11 matrix, where again I get to cut out some things. And when we do the substitution for this function, right, then, yeah, as I already said, C goes to this, and A goes to the Jacobian matrix of the function. And you compute these Euler characteristics, you get petty numbers. And yeah, it's actually very simple. Most of it is zero, right? So in this
Is
case,
this like just happens? Or do you get like non-zero terms in several places?
in this case, it's not too much of a surprise that these are all zero because effectively we're dealing with the classical complete intersection case. So we're not, with this example, we're effectively not going beyond original Le-Greuel setting yet. But that's, of course, the question: do we find spaces where there are non-trivial correction terms?
If you have like 4 is equal to 5 minus 1.
The Betty numbers.
The Betty numbers, yeah. I mean, you can have Betty numbers. In this case, you don't, but I just imagine that for an order characteristic equal to 4, you may be realized as an alternating sum of integers.
Yes.
But it's interesting if
But
that.
has each number kind of topological interpretation on intermediate spaces?
That's another question.
That you could say there you have this kind of rectified depth condition, so which guarantees from geometric reason that some pieces are concentrated.
Yeah, that's all things to explore. The problem is that this complex is coming out of a really long baking process, right? So if you take the raw output from Czech homology, I have another example, like 2 slides ahead. You get modules which are not of rank 18, but of rank 180,000, right? And then you do Gauss reduction of this complex, simplifies the complex up to homotopy, and you end up with this. But that obstructs the interpretation of what you're actually seeing. But of course, what I'm hunting for is find some spaces where you see more phenomena and interpret them. So, if you remember my Le-Greuel type formula, they have 2 terms for every induction step, one with a plus sign, one with a minus sign. And for the other one with a minus sign, instead of taking this second component of the function g, we have to do with the generic linear form. And we do that, and we get these Betty numbers. So there is a correction term. And for that correction term, I do have an interpretation. Right? So no intrinsic correction terms in this complex itself yet, but from the 2 different complexes. So in this case, I can show you where it comes from. So if you remember this, this stratification, this is now the hyperplane section by the first component of G of this generic determinant of rate. The example has been chosen so that this fits with this final example of the complete intersection. So we're not in a hypersurface case actually, because we already took one hyperplane section from higher dimension. So this is what we actually want to measure. One most critical point. This one doesn't count, it's on a lower dimensional stratum. Here's the other most critical point. So we want to have 2. Right? So what does the complex measure? It doesn't measure on the central fiber, it measures on the generic fiber. So if we take this generic fiber, this is smoothed out, then we get 1, 2, 3, 4 most critical points. So 2 more than we actually want to measure, and these 2 here and that one, they are coming from what happens for a generic linear form. And that's what the correction term computes.
Those powers you put there, are they some polar numbers or something like this? In your complex. For hypersurfaces, I assume this is just the singular, the chain complex, or the leg complex, or whatever they call it.
Yeah, it's relative polar.
Yeah, so these are all relative polar numbers.
Now for the other complex, I mean, I showed you 2 formulas, right? But I only treat the one in the beginning for which uses falsifications. But for the other one, it's polar numbers, yes. So no real surprise, but I hope to to bring some new flavor with complexes and some computability. Okay, so this is a candidate where I hope to be able to do something more general or to see some new phenomenon. So this is a space which is not a complete intersection, so it cannot be treated with the classical Le-Greuel formula. You don't have a chance. And if you consider this function, and very similar, right? But this is a rational triple point from Thuringer's list. In this case, we know from the computations by Thuringer already that this is has a Milnor fiber, which has this has a unique smoothing, this singularity, which is a bouquet of spheres, k plus L minus 1. So we know what the complex link is. We can subtract this according to the bouquet decomposition, and then we see, okay, whatever we get out of these magic complexes, it has to add up to k plus L minus 2. And I tried to do these computations with Oscar. Up to now, I have implemented a naive Czech homology computation, and these are the numbers I get. Homological degree -9 is still tame, and I get to 18, and it gets nasty. Right? And here you do Gauss reduction over polynomial ring in 12 variables with matrices of this size, and it's tricky. So I think we have to improve the algorithm. We can't do it the naive way. So I didn't have the patience to let my computer run sufficiently long, but I think I computed up to here. Up to here, the complex is actually homotopic equivalent to the zero complex. So everything you see here cancels already. Right? And then it starts to slowly get interesting, but you expect something like rank 1, rank 11, rank 9, nothing more. That's what you get. Okay, so I think that's it for the moment. Thank you very much.